Yeah, it's great to be here. As some of you probably know, my co-founders are German, and I'll talk about that in a little bit. But they've only taught me inappropriate things to say in German, so I can't share. Okay, I'm going to be talking a little bit about how you can use Dcos to be really doing a lot of data processing as well as run containers in a cloud agnostic way. So this is kind of an overview of the presentation. I'll talk for hopefully about 40 minutes, and then I'll leave a few minutes at the end for some questions. We're going to talk about sort of this new data-driven architecture perspective, how you can get to a place where you can get a cloud-like experience, but really on any infrastructure, why you'd want to use something like Dcos to run all the services that are part of the SMAC stack. And if you hadn't heard of the SMAC stack, I'll talk about it. And then a little bit of Dcos in action, and maybe we'll even play a video at the end of seeing it go. So I wanted to start, also, you're seeing the PDF version of the presentation. So there are a couple slides that have animations, which you won't see here. So I'll talk through it all. Just be prepared. You might see something on the slide that I'm not talking about just yet. So I wanted to start with really talking about this architectural shift that I really saw firsthand when I worked at Twitter, and we really saw in Silicon Valley that I think a lot of other organizations are working with now as well. And it's this move from this what we call the traditional application on the left, this gray circle over there, where a lot of organizations had singular monolithic applications, maybe some database that they were communicating with, and then users who in many cases were the employees of their organizations that were communicating with those traditional applications. And a shift from this world to this new world on the right, where the number of people that are actually consuming these applications is far greater. It's not just employees within the organization, it's also customers and users, because these organizations are providing this as a service to everybody else, as well as the kinds of applications are moving from this monolithic application to microservices, to many different instances of the services that have to get deployed and managed. And on the back end, the amount of different kinds of data processing that people are trying to do is ever growing in complexity. And I think the crux of the entire presentation, really, what we're doing at Mesosphere, is on the left, the world wasn't so bad. It was pretty manageable. There's a black box, there's a database, there's not too many users, latency isn't too high. And on the right, the world is pretty crazy, right? Lots of arrows, things communicating, many instances of this service. And the whole point of what we're trying to do at Mesosphere is say, as you make this transformation as well, you really want technology to help you manage and automate a lot of this work to actually do this. Okay, so for most organizations, success looks like, I got to ship my code quickly, and I got to take advantage of new data technologies because I want to do more interesting things. And so for us, really what we've seen a lot of organizations in Silicon Valley and other places, the way we've seen them tackle those success requirements is really this twofold approach. One is microservices, as I mentioned earlier. Break up your monolithic applications into many different independent microservices and containerize them. So we just heard about containers. Take those applications, stick them in containers, and then get them deployed and managed throughout the infrastructure without humans really having to be involved. And the other side of it is really big data services in general. Things from analytics to databases to distributed file systems that are going to help us do more sophisticated things with the data we actually have. So this one on the left, I think, is how a lot of organizations enter into thinking about this new way of potentially running their applications. But the one on the right is really critical, because the one on the left is arguably a little bit easier to manage than the one on the right. The right has stateful services. You want these things to be incredibly elastic. And so a stack has really evolved for thinking about the things on the right. And we call it the SMAC stack. So who's heard of the SMAC stack here? A bunch of folks. So I'm going to talk a little bit about it. So SMAC, the acronym stands for Spark, Mesos, Akka, Cassandra, and Kafka. And kind of like the LAMP stack, which is a stack that emerged that helped organizations really think about how they wanted to deploy their web applications, where LAMP was Linux, Apache, MySQL, and PHP. SMAC has really emerged as saying, okay, well, I'm going to need something to manage my my events that are coming in. So I've got this feed of information, events that are constantly coming in, so I need something like Kafka for that. I want to do analytics on it. I want to both do real-time analytics as well as batch analytics, so I'll use something like Spark for that. I need to be able to store this data in a distributed way across multiple data centers, across the entire world. So I'll use something like Cassandra for that. And then I want to build these microservices that I was talking about that are actually going to then be going to be using the data as well as interfacing with humans for providing whatever service I'm trying to build. And just like in the left, where the LAMP stack was focused on Linux being the thing that was going to help you manage all this, what we're trying to do at Mesosphere is say Mesos, and in particular Dcos, can be that thing that can help you manage all these things. Because they're complicated. They're not easy to just spin up and run on your own. In fact, they're so complicated, most of these distributed services, most of these distributed applications are so complicated that there's entire books that are devoted to them. When you want to take on one of these services and actually deploy it in your environment, you probably are going to go and be buying that book and reading about it to actually do that. And I'll talk about that in a little bit. And so one of the things that the cloud has done, and the cloud promise that has made this really successful, is they've simplified the way that you would consume a service like this by providing a SaaS offering of it. Right? They said, oh, you want a message queue? If you go someplace like AWS, you can get that message queue by clicking Kinesis. Right? You get the message queue. Oh, you want a database? We'll give you DynamoDB. And so you get this experience of deploying these applications and running them in a very, very simplified way from an operations perspective. But then you're moving to the cloud. And so there's kind of this fork in the road. So now I'm going to talk about that. So really what we'd like organizations to be able to do is get that cloud-like experience, but from any infrastructure, to not have to be potentially locked into a cloud. So getting back to that fork in the road, this is what a lot of organizations sort of get to. They say, well, we can do it all ourselves. We can buy all those O'Reilly books. We can read about all the services. We can figure out how we're going to set it together. We're going to run many of these different data services on our own infrastructure, potentially silos within the organization. So, in many circumstances for orgs, that tends to be slow and complex. It's siloed and inefficient, but the pro is you have complete architectural control. You can decide how that's going to evolve for you in the future. Now, with the cloud provider model, you say, well, I can get these services with a click of a button. As I mentioned, I just get Kinesis by clicking a button, but the cost is much higher, and you really end up being tied to service providers. And this is what a lot of organizations do when they first move to the cloud, is they say, yep, I want all these different services, and eventually they end up using those services and getting completely tied into then being locked into that specific infrastructure. Right? So, and these guys are all fighting. They want to keep you in their own cloud as much as possible because they would like to grow, and we don't want to have Oracle all over again, right? So maybe this is actually a false choice. Maybe you could get the same data center-like control and the cloud speed, and that's really what we're trying to do with the DCOS, is say, let us provide a platform that gives you that same cloud-like experience, but now you can run it on any infrastructure. You could run it on a cloud, you could run it on multiple clouds, or in fact, you could also run it on your own bare metal data centers, okay? So, and the whole premise here is, move from a world where you're kind of managing the individual silos in the build your own approach, and just run a single, what we call DCOS, the data center cloud operating system, for running all your services on top. So pool everything into, I think Henning called it a supercomputer. I don't speak German, but I think I saw that word on the slide. And he also told me ahead of time to manage your infrastructure. So at the core of that is really a project called Apache Mesos, which really acts as this cluster manager. And then DCOS is a bunch of other functionality around that. And just like, using the Linux analogy I used earlier, DCOS is like our Ubuntu or our Canonical or, or our Debian, which wraps Apache Mesos and provides it for you to be able to use in your own environment. Okay. So now I'm going to, since when I was asking originally what was going to be, the best level of presentation, I said kind of a mix, some little bit high level, what we're trying to do, as well as maybe get a little theoretical. So this next part of the presentation is where the nerds parts comes into my presentation, the talks for nerds part, where I'm going to go be a little bit theoretical about, why Dcos for something like the SMAC stack? Why did we build Dcos the way that we did, and why does it end up working really well for SMAC-like services? Okay, so the approach we took in the Dcos and the approach that we took in Mesos is this concept of what we call a two-level scheduler. Okay, so the idea is getting back to that picture that I showed earlier. The flywheel of success looks like running your microservices and containers as well as running your data services. You can do that by running your containers using something like a container orchestrator, and you can run your data services via sophisticated data service orchestration. And so since these are very, very different ways of thinking about how you'd actually run applications, the mechanism that we built into Dcos is something that we call two-level scheduling. And I'm going to get into details in the next, I think, 30 slides, they'll go fast, about exactly what two-level scheduling is and why it ends up being really interesting. Most organizations that are just using container orchestration but are not also trying to take advantage of the data orchestration that we do are going to end up running their data services outside of the platform. And at the end of the day, you want to run everything inside of the platform so you can benefit from economies of scale, both from a management perspective as well as a efficiency, utilization, and cost perspective. Okay, so this is the typical flow that a lot of admins, ops folks, do when it comes to running some new data service. Right? This is their algorithm. Like, all right, I got to download it. Then I'm going to deploy it, then I got to figure out how to monitor it, then I obviously need to maintain it because if something bad happens, I got to fix it, and then step 5, I got to upgrade it, which means I got to go all the way back to step 1, and I have to do it again, right? All right, so downloading is pretty straightforward. Everyone knows how to do that. You go to the web and you download it. Now let's move on to the deploy step. So how do I deploy this thing? Okay, well, what do I do? So I got to start thinking about all these different constraints for how to run this service. What are the fault tolerance needs for this service? How do I have to deploy this and run this in a way where it's fault tolerant? What are the high availability needs for this service? What are the latency requirements? This is a distributed application. This is a distributed service. What are the latency requirements in terms of how it's communicating with one another? What are my bandwidth requirements? How much CPU or memory does it need? So forth and so on, right? And ultimately, once we gather all that information, that gives us some configuration that we can then use to decide how we're actually going to deploy this. That was the whole point of this step, right? Deploy. So how do most of us actually figure out how to do this? We buy the books, right? I told you I'd come back to the books. We go and we buy the books and we say, all right, well, to deploy this, I'm going to read about all the different things that tell me about how I'd actually want to deploy this at scale in production for my organization. Okay, so I get all that information, and now I turn that configuration into something that I ultimately want to express into some tool to make my life easier when it comes to actually getting it deployed in production. Some of us, many of us, still don't do this step. We actually go to individual machines and we just install it and hook it all up completely manually. But many of us have at least taken one of the first steps of automation, and we've introduced something into our organizations like Chef or Puppet or Ansible. Or perhaps we're already using something like Marathon on top of Mesos, or Docker Swarm, or Kubernetes. Okay? And the step here is once we're expressing our configuration to one of these systems, then they go ahead and they say, well, okay, now I'm going to orchestrate it. Now, based on that configuration you gave me, I'm going to figure out how I'll orchestrate this across whatever number of machines I have. So here we go. This is getting installed on these couple machines, and they're going to be configured so they can actually communicate with one another. Okay, so that's the deploy step. Everybody with me? This is a pretty typical flow for lots of admins, lots of ops folks for how they're actually doing deployments. Okay, of course, we don't have to do it once. We have to do it many times, right, for each of the different services that we're actually trying to deploy. Okay? Now we get to the next step. Now we need to monitor it. We don't have to monitor it, but if we don't monitor it and it happens to go down in production, that's not a good thing for us or our customers. So of course, we're going to probably monitor it. So how do we monitor it? How do we figure out what to monitor, what's important to think about? we probably go back to the book, right? We go back to the book and we say, okay, what's important in the book? We find that out. And then we set it up. And maybe we use something like Nagios. Anybody here used Nagios before? A couple folks, okay. This is a bad day for a Nagios user. There's a lot of red. Stuff is not going well. So now we got to debug. Not a good day for a Nagios user. I got to figure out what's going on, so I got to debug. What do? I probably go back to the book right? To start learning what possibly could be wrong by going and reading the book again. Maybe I go to the internet. I ask some people for some help. What possibly could be going wrong? I probably find what's going wrong by going to the internet. There's probably something on Stack Overflow or something else that tells me what I did wrong. So I fix it. Right? I'm like, oh yeah, I did this thing the wrong way. I got to change this thing. I didn't realize that if this machine fails in that way, I have to bring up the other service in the other way. So I go ahead and I fix it, right? All's good, right? I fixed it. Everything's okay. Except I get the exact same error the next day because the way that I fixed it wasn't going to survive a machine reboot, and the machine rebooted, and now I got the exact same error all over again. Now it's 4 a.m., and I'm like, WTF, why am I doing this to myself? So I got to fix it again, except this time I'm like, when I fix it, I'm never going to, I'm going to do it right this time. I'm never gonna suffer from this same outage again, right? And this probably doesn't happen once or twice. This probably happens many, many, many times. And folks that have operated these systems in production know exactly what I'm talking about. You know about those 2 a.m., 3 a.m., 4 a.m. Times when you're actually working through this stuff. Now I got to upgrade it, and I got to do this whole thing all over again, because who knows what's changed across these versions, right? So, the thesis that we really have when we were first building Mesos and what we used throughout Dcos is that distributed applications, these distributed systems, they should be able to operate themselves. They should be able to deploy themselves. They should be able to monitor themselves. They should be able to recover from failure themselves, scale up, scale down, upgrade, so forth and so on, right? And there's really two core reasons. The first is because operators have inadequate knowledge of the distributed application's needs or semantics to make the optimal decisions when it comes to actually operating them, right? We just don't know all the things we might potentially need to do to make this work, even after reading the book. We still don't know, right? And the execution needs and semantics of these systems, in many cases, can't easily or efficiently be expressed to the underlying system. I can't tell Chef in some configuration, or Puppet, or Ansible via some configuration what to do in all these circumstances when stuff goes bad. I don't have the ability to actually express that. And vice versa, and I'll get back to that and vice versa in just a little bit. So the example that I love to use for this is Hadoop. So, how would I take something like Hadoop and express it via some configuration that I could then give to something to orchestrate in the most efficient, most fault-tolerant way in my data centers? And for those of you that have never run Hadoop, it's MapReduce. So it's first phase is map, what they call map, where you're doing a bunch of computation over a bunch of data, and then reduce. There's this special phase in the center called shuffle and sort, which is probably one of the more complicated phases. They really should have called it map, shuffle, sort, reduce. But that's a mouthful, and that wouldn't have gone as well. But the point of all this is that there's this configuration spectrum of how you might want to run some complicated distributed system like this. And if you configure it in an extremely coarse-grained way, it's probably pretty easy to express. You're like, just give me a machine for this thing. And that's how most of us would do it, right? We'd be like, well, just give me that machine. I'll just use whatever resources I have. If you try to do it in a fine-grained way, it's pretty much impossible, because it's such a complicated distributed system. To actually express in a fine-grained way how to most efficiently run something like this is nearly impossible. Basically, it would need software to actually do it. Right? Now, the fine-grained way would give us the best possible utilization. It would manage everything the best we could, but as I said, it's very, very hard to do. This is not the end of my presentation. There we go. So, the critical question that we really wanted to ask was, why can't Hadoop decide this for me? Why am I having to try to figure this out? Why can't Hadoop just do this for me? The crux of this is that, why can't it do this for me when applications, they really operate themselves on Linux. The applications we write They operate themselves. What do I mean by that? When an application that I write just on Linux, when it needs more resources, it asks the operating system for more memory or more CPUs. It can't actually ask for more CPUs, but it can create another thread, and the operating system recognizes from that that it's going to run in parallel. When it needs something like a file, it asks the operating system for a file. So we build our applications to really operate themselves. We just don't build our distributed systems to actually operate ourselves. The application effectively has this interface between itself and the operating system, what we call the Syscall interface, which provides all this functionality for the application to be able to effectively operate itself, to do what it needs to do, right? Now, this didn't always exist. Just like it doesn't exist today for a lot of distributed systems and distributed applications, this didn't always exist. And if you go back to the early days of Windows, does this look familiar to anybody? I realize that my color scheme is not great. It might be hard to read some of these texts. I apologize for that. This is basically, this is taken straight out of how, for those early Windows programmers, how you'd think about how you gave resources to the Windows applications. So the way in which you ran early Windows programs is you actually told each program how much memory it would be using. In fact, you didn't just tell it how much memory, you actually told it which range of memory, because it was actually using that physical memory. And the applications got it wrong all the time. They would write on other people's memory, or they'd write past their memory, and stuff crashed all the time. Right? And then eventually we said, hey, what if we introduce some better abstraction in the operating system world, where applications themselves, when they wanted more memory, they would call into the operating system and say, hey, I need more memory, and then that would be provided, versus humans constantly managing the memory. So, if this looks a little bit like that picture I had before of us basically statically partitioning and deciding how stuff would get run in a really static way, it's because it is. So, how can we actually do this? Well, distributed applications themselves, they need some kind of an interface to be able to communicate with the underlying system, as we said before, and vice versa, which I'll get back to. So just like applications have the Syscall interface where they can call into the operating system, the distributed applications need something similar where they can do things like say, hey, I need more resources, or I need less resources. Hey, can you launch this container, or can you launch this VM? Hey, I need you to create some storage. I need you to attach or detach that storage, so forth and so on. Okay? Now, I talked about this vice versa. I said, these applications need this interface between themselves and the operating system. But I also said vice versa. What's this all about? So this is where we're getting especially nerdy. And it's this idea that operating systems should be able to call back into applications as well. This kind of has nothing to do with my talk per se, but it has to do with what we've built in Mesos and why it's so powerful for organizations like you to take advantage of. Wouldn't it be great if operating systems could actually call into applications as well? Right? So the analogy I like to use is today, when an operating system decides to page out an application, it does LRU. It decides the least recently used memory of that application is what it's going to take out from main memory and swap and write to disk. Right? The reason it does LRU is because it doesn't know any better. So if you're running an application, which we often have with AI and ML and other analytics, where you're just circling through memory, the operating system is doing the absolute worst possible thing for you when it comes to swapping out memory, because you might go to touch a memory that just got swapped out. You might go to touch a memory that just got swapped out. You might go to touch a memory that just got swapped out. What if instead the operating system could ask the application, hey, I have memory pressure and I'd like to get some resources back? And then the application should say, yeah, it makes a ton of sense. I understand you have memory pressure. Why don't you take this page? That's the farthest in the future I'm going to actually be touching. Or why don't you take this or whatever else it is, right? There's a bunch of examples like that we can't really do in traditional operating systems because we don't have this bidirectional mechanism. But that's something that we wanted to actually build into what we're doing with distributed systems as a critical part of the operating system being able to call back into this distributed system as well, to be able to say things like, hey, your containers have failed, or to be able to do things like container deallocation, resource deallocation. This becomes especially valuable when you're trying to run some of these stateful services, which are writing state to disk and potentially need to get moved around the cluster when you want to do things like maintenance, or when you want to do things like better bin packing, what we like to call defrag. It's the modern defrag. We're bringing defragmentation back because you want to do something like that in your data center environments as well. How do you do that without this bidirectional communication? So, The way we like to think about it, this bigger picture, is that abstractions between, say, operating systems and applications, they exist for good reason, but without sufficient communication, they really force suboptimal outcomes. And I think this is just a general tautology. I think you can replace the word abstractions with pretty much any word, and the sentence still makes sense. So the one I like to use is management exists for good reason, but without sufficient communication, they force suboptimal outcomes. Right, so it's a good one. Okay, all right, that joke didn't land too well. All right, so we'll keep going. So what we effectively built to solve this bidirectional interface for these distributed applications was Apache Mesos. That's really the history and the theory behind why we built Mesos and why we built it the way that we actually built it. And you can go all the way back to some of the research papers, which is where Apache Mesos started. So for us, the way that we've been able to take advantage of this two-level scheduling is by being able to say, take these different distributed applications, have them leverage this API for two-level scheduling so they can operate themselves, so they can run in much more automated ways, so we don't have to go buy the book, or if we do have to buy the book, there's a much smaller chunk of the book that we actually need to read to actually run these things. And again, this is a big part of what we do at Mesosphere with the Dcos, specifically with the SMAC services that run on top. So here's just a collection of some of those services. Things like Spark for analytics, Kafka for stream ingestion, for key value stores, Cassandra, for relational databases, MySQL, Search, Elastic, things like caches, Redis. And again, getting back to what I talked about earlier, so that you don't have to take this fork in the road between doing it yourself or doing it via cloud services, our goal is really to be working with an ecosystem and partners to take these things and provide the AWS or cloud equivalent services so you can do this on top of our platform on any infrastructure, across multiple clouds, in your own data centers, in a data center, on a cruise ship, which I'll talk about in just a second. Now, because we have this flexibility, we're also capable of running multiple different kinds of container orchestrators. There's been many, many different container orchestrators that have run on top of Mesos in the past. One of the earliest ones was Twitter's, a project called Aurora, which is where I was for many years. Then at Mesosphere, we built one called Marathon. Apple had built one called Jarvis. Netflix had built one called Titan. And we've also taken Kubernetes to run on top as well. So the point of this is not to say, go look at all these things. It's more just that this flexibility has enabled a lot of organizations to be able to actually do this. All right, Dcos in action. Mesosphere as a company really came out of the open source Apache Mesos project that I was talking about a little bit earlier. In about 2009, 2010 is when we first started working on that project. The founders, as I mentioned earlier, are two Germans and myself. Flo and Toby are my co-founders. They're from Schweinfurt, Germany. I don't think that's too far because I once in high school came to Germany to visit Schweinfurt when I was doing the reverse exchange, because Flo, my co-founder, was actually my foreign exchange student in high school. So we met each other a long, long time ago, did a bunch of nefarious things with computers at our high school, and then eventually, many, many years later, he was working at Twitter, where I was also working. We worked together to help basically build out Twitter's private cloud. Then he went on to work at Airbnb, where one of his colleagues, Toby, who's also from Schweinfurt, was working. They went out to help build out Airbnb, and then together we came together to found Mesosphere. Our product is, again, as I mentioned, is Dcos. There's an open source version of it that we made available in 2016. So just a few words about really what we're doing at Mesosphere. For us, the reason why we really founded the company is because we saw this just outside of Twitter and Airbnb as well, which is this widening gap between most organizations and tech companies in Silicon Valley that were taking advantage of the new technology, and this need for organizations to really be going a lot faster technically, to have heart speed, as Henning mentioned. And the competitive landscape getting really, really blurry. One day Amazon is a bookstore, and the next thing you know it, Amazon is a grocery store. And with all that happening, you really need to be taking advantage of technology to go faster. So a couple of examples of different ways in which organizations are able to take advantage of the technology to run containers and data services and generally move faster. Companies like General Electric, who collects tremendous amount of data on all of their sensors and want to be able to use that information for being smarter about how their services are actually running. Companies like Audi that are building the connected car, obviously there's lots of data coming in there. Companies like Royal Caribbean, a cruise line, surprising to see how much data they actually collect from all of their users walking around on the boat, going to different shops, and how they can give a more tailored experience if they can take advantage of that data. And then hedge funds like Two Sigma that obviously want to use that data to make the best decisions they can when it comes to their investment strategies. There's other organizations as well. I won't mention them by name, but if you go and you see some of the organizations that spoke publicly at MesosCom, there's a big bank that talked about basically how they're creating their internal cloud because they want to provide that exact flexibility I was talking about, which is the ability to get a cloud-like experience, but on their own private data centers, as well as across multiple cloud providers at the same time. So they have many, many different business units that are all sitting on top of effectively this cloud to be able to leverage and get the same one-click experience for getting message queues, databases, analytics, so forth and so on. Okay, and then the other one that I mentioned, I said I was going to briefly chat about, is something that we're also really excited about, which is where data centers don't typically exist. And I think we're going to start to see a lot more in the future. So, the best example is the data center on the cruise ship. Yes, there are data centers on cruise ships, and they are running a lot of different kinds of functional workloads. And so organizations are starting to have to think about how they want the way that they deploy and manage their applications in the data center on the cruise ship to look exactly the same as how they're going to do it in their own private data centers to look exactly the same as how they're actually going to do it in the cloud. And so it's very interesting to see organizations also be able to take advantage of the platform to do things like this. For me, I think one of the things that I expect we'll see a lot more in the future is this notion of what many people are calling edge computing, which is this idea that we kind of all have been dogpiling in the cloud for doing all of our computation, but when something like a plane lands, when an Airbus lands and it's got a GE engine, I actually don't know if that's a thing, but I assume it is, and that engine has a couple terabytes worth of data that you want to process, there's no way that we're going to be shipping those couple of terabytes up into the cloud. We need to be able to do that processing right there at the airport in the edge where we can get as much information as we want. Maybe we'll still send some data back other places, but we need to have the flexibility of being able to stand up and run these kinds of infrastructures wherever we want to. Okay, so I've got a couple minutes left, and what I thought I would do is I would attempt to play a video, but I might not be able to. We didn't try this part ahead of time. Okay, if it's not possible, it's not possible. I can break a little earlier for questions. Basically, this is a video, and for those folks that are interested in the video, we can share the link to the video. But it's basically just a video that's sort of walking through this experience, where in that video we bring up all of Kafka and Spark and Cassandra. We launch a Spark application. We scale the things up and down. We kill some machines, and you see how all this continues to run without human intervention. Okay, so let me do this. Let me wrap it up there, and I know we wanted to stop at the end for some questions, so I'm happy to answer questions.
Thank you for the talk.
Yeah, thank you.